All right. So my name is Ethan. I am a third-year undergraduate, and I've been doing research under Daniel with another undergraduate, Yuval, who's in this call. And Yuval and I, we've been trying to figure out max cut on unit interval graphs. We've been trying to come up with an algorithm or trying to prove that it's NP. And the research paper that really kickstarted this project for us was this paper that I'm going to be going over this class. And this paper is time complexity of max cut on interval graphs. There is a reduction to show that it is NP complete. But just like a little bit of history, that's kind of funny. So yes, so starting out before 1999, both the max cut on interval graphs and max cut on unit interval graphs, they were both open problems. But then in 1999, all of a sudden, unit interval graphs, an algorithm was found for them in polynomial time. But then just 5 years later, this paper was actually proven incorrect with a counterexample in this paper. But fortunately, yeah, a few years later, all of a sudden, unit interval graphs is one more time solved in polynomial time until just a few years later, it was actually, the counterexample was found for it. So not good in this paper. And then starting in May of this year, Yuval and I began doing research on the time complexity of interval graphs. So not unit interval graphs, but just pure interval graphs. But then one whole week later, all of a sudden now the problem that we were working on, time complexity of interval graphs, was solved with this paper that we are going over this class that says that interval graphs are NP complete. So this is a very active problem. Yeah, so after that, then Yuval and I decided to not work on interval graphs, but we instead are working on unit interval graphs. So hopefully we can publish something that will not have a counterexample this time, like the previous two papers. Yeah, so this paper, we are going to be reducing max cut on cubic graphs, which is NP complete, to max cut on interval graphs. So yeah, quick definition. So a cubic graph is any graph where every single vertex has exactly 3 neighbors. So here, oops. So here's a cubic graph because this vertex has 3 neighbors and this vertex has 3 neighbors, this vertex has 3 neighbors, or this one, this has 3 neighbors, 3 neighbors. So yeah, cubic graph, every single vertex has 3 neighbors. And so also, so here's an interval graph. So an interval graph is an intersection graph of intervals on the real number line. So you have all these intervals here of any length. Every single interval corresponds with one vertice, and an edge exists between these two vertices if they intersect on, if their intervals intersect. So we can see this red intersects with this orange, so therefore there's an edge between them. But this red and this blue do not intersect, so there's not an edge between them. And yeah, so another case here, every single interval intersects with every other interval. So therefore we just have a clique because every single vertex has an edge with every other edge. Max cut problem. So yeah, the max cut problem is performed on some graph, and a cut is a partition of the set of vertices into 2 disjoint subsets A and B, and the size is the cardinality of all the edges that have one endpoint in A and one endpoint in B. So in other words, if we have this graph right here, if we have this be one subset and then this be one subset, then the cut size will be all of the edges that have one endpoint in A and one endpoint in B. So here's one edge and here's one edge and here's one edge and here's one edge. So this cut size will be 4. And the max cut problem says we want to try to maximize the cut. So we want to find some arrangement of all of the vertices into 2 disjoint subsets such that we end up maximizing this cut. And here, yeah, as another example, here's the max cut of this graph. Like a lot of people may think like, oh yeah, this is the max cut. Like best you can do is cut 3, but you can have like this be a subset A, and then like have like this be a subset B. Yeah, max cut is a well-known just NP-complete problem, and is NP-complete on cubic graphs. So we're going to be using the fact that it's NP-complete on cubic graphs and reduce cubic graphs to interval graphs. Here is a cubic graph, and we need to assign every single one of these vertices and every single one of these edges a gadget. And a gadget is, in this case, is just going to be some interval graph that takes on this shape, where each one of these are like vertices and they overlap in some way. And then, so we're converting this into some unit interval graph using a bunch of these shapes that are all lined up like this. So like, for example, so all of the vertices will take on this gadget shape where you have all these left long intervals and all these right long intervals, and all these left short intervals and all these right short intervals. And note how all the long intervals intersect with one another right here, but none of the short intervals intersect with anything other than their long intervals. And so what we do is we make a gadget for every single one of these vertices and for every single one of these edges. And we assign some arbitrary ordering to all of them, and we put them all in a line. So I'm saying here, we're going to put this red gadget right here, and then we're next going to put the blue gadget, and then next we're putting the brown gadget, and next we put the green gadget. Once we've done all the vertices, then we do all of the edges. And I'm going to be calling these like E gadgets or V gadgets, depending on if it's a vertice or an edge. Okay, what is P and Q? Yeah. So yeah, I'm lying a little bit here. So these lines right here is just like a shorthand notation, because what each of these lines represent is actually like a bunch of different intervals. And the number of intervals there are exactly Q. So there are always going to be, for every single gadget, there's going to be like Q brown interval, long intervals, and like Q red, and on both sides, and P is the number of short intervals there are. So Q is number of long intervals, and Q is the number of long intervals, and P is the number of short. Yeah, so P and Q are the same for all of the V gadgets. So all of the V gadgets have their own P and Q, and then all of the E gadgets have their own P and Q, P prime and Q prime. Yeah, and so we choose P and Q in a very specific way, especially for the backwards direction. And yeah, we'll go over it in a minute. But just for now, just consider them arbitrary numbers, P and Q, and then P prime and Q prime. Yeah, okay, so we take this cubic graph, and then now we go and split it up in all these gadgets. And each of them have P and Q and whatnot. Okay, let's move on to the next step in this. So the next step, we have to add link intervals that go and connect to these gadgets in some certain way. And this reduction says that for every single V gadget, we want to go and connect it with a link interval all the way to whatever E gadget it has as an edge. So like this red vertex right here has a pink edge, a gray edge, and a purple edge. So we can see it has a link interval that goes to this pink one. It has a link interval that goes to this gray one, and it has a link interval that goes to this purple one. So, and like, for example, like, so yeah, this brown one has a link interval that goes from the brown to the gray, because there's gray edge, and then, yeah, brown to purple. Yeah, so every single V gadget has some link interval that connects it to an E gadget. And, but if you notice, yeah, some of these e-gadgets, or every single one of these e-gadgets, is connected in a slightly different way. And let's just look at this very first one, this pink e-gadget. So this link interval ends right before the first short interval, and then this one ends right before the next long interval. And that's very important for what we do later. And the way that we determine which link interval is like intersects with all of the short intervals and which one like does not is the one that ends shorter is always first in this arbitrary ordering. So like here, yeah, this red one is first, so therefore this is going to be the one that ends sooner. Or like here we can see that on this green one that the blue one is first in the arbitrary ordering, so therefore the green one is going to be longer. This is the entire reduction. This is how we go from a cubic graph into a unit interval graph. So this is what the unit interval, or sorry, not the unit interval graph. This is what the cubic graph to interval graph looks like. So now, in theory, when we take like the max cut of this, now we will know the max cut of this. And like if we take the max cut of this, then we'll know the max cut of this. Here I wrote out what the max cut of the cubic graph could be. And yeah, very simple for just a clique, you just cut it straight in half. So we have that, I'm going to say that this blue one is on side C and this red one is on side C. And I'm going to say all of the ones that are on side C are going to be highlighted in yellow. And also, so when we go and take this cubic graph and then we boom, turn it into this interval graph. Now we are, all of the yellow highlights will represent side A, and whenever there's not a highlight, that will represent side B.
Wait, can you, so let's see, C and D is always in the original, like the graph you're reducing from, right. A and B is always in the graph you're reducing to.
Yes, for this reduced graph, all the items that are in partition A are going to be highlighted, and all the ones that are in partition B are not going to be highlighted. This paper tells us that, so for every single vertex that is in C, in the original cubic graph, we want to put all of its right short intervals and left long intervals and all of its link intervals into B, and all of its left short intervals and right long intervals into A. And so like if we look at this red one, so it's in C, so therefore we take all of its right short intervals, which are right here, these top ones, and we put them into B, meaning like we don't highlight them. And then we take this left long interval and we also put that in B, so therefore it's not highlighted. And then similarly, so now for a vertex that is in D, so let's take this brown one, we put all of its right short intervals into A, so we highlight them, and we take all of the left long intervals and we put those in A, so we highlight them. And we take all of the link intervals and we highlight them, we put them in A. So here are all the, here are the three link intervals that intersect with this gadget. So we go and highlight them and put them in A. And so now we've applied coloring to all of the link intervals and all of the V gadgets. All we have left is just this section right here, which is the E gadgets. So let's do that in the next step. And once again, it feels like a little bit arbitrary, but let's just follow what the reduction says. So it says we take whichever interval is slightly longer than the two. And if this is yellow, if this is in yellow, then we put the left long in yellow and the right short in yellow. So yeah, we see like, oh, okay, yeah, this one is yellow, so we put this in yellow, this in yellow. We see this is in yellow, so we put this in yellow, this in yellow. See, this is yellow, so we put this in yellow, this in yellow. But here's one where it is not yellow, so we do the opposite, where we put just these inner ones in yellow.
So what is the rule for the link intervals? When do you color them yellow?
You color them yellow if the vertex that they are connecting to is in D.
Okay. So this is a rule you apply to all link intervals. So like if the vertex it ends in is in D, then that was going to be yellow.
Yes.
Okay. Now there is a rule for edges. And there are two different rules, right? Like one if the edge is cut and one if the edge is not cut.
Mm-hmm. We have not considered whether an edge is cut or not yet.
Well, cut means cut. I mean, it's like cut or not just means one of them is yellow. Is precisely one of them yellow, in which case which one, and whether both of them yellow or are both of them white, right? This is basically distinguishing whether the edge is cut or not, but it also has two subcases in it.
Exactly. Yeah. So in the next step, I talk about like what we've just discovered, which is what Daniel just said. That so let's look at like this purple one that was cut. So it's this one right here. We can see that since it is cut, there is one that is colored and one that is not colored. Or for like this one that is not cut right here, we see that both of them are colored, meaning that both of their edges are going to be on the same side in the cubic graph. So if the two link intervals that connect with an edge, if they are the same color, that means that both vertices are going to be on the same side. Therefore, that edge is not going to be cut in the cubic graph. But if the two link intervals that connect with an edge have one that is colored and one that is not colored, like this case, then that means that the two vertices are on different edges, so therefore it will be cut.
Can you just repeat whatever you said slowly?
Yeah. If a e-gadget has two link intervals that are different colors, that means that the two vertices that this edge has as its endpoints are in different sections.
Mm-hmm.
So yeah, like this green guy, this line right here. So we see that it has a vertex in C and it has a vertex in D. And we can see that, so therefore it will be cut. And we can see like the one that is in D is highlighted and the one that is in C is not highlighted. Therefore, this particular e-gadget will be cut. Whereas, like say this one, both of the e-gadgets are colored in the same way, meaning that the vertices that connect to it are going to be in the same spot. So here, like we have blue and we have red, and we can see, oh yeah, look, here the blue and the red one that are connected by this purple one is not going to be cut because they are colored the same way, meaning like they are on the same side. So the coloring, it feels a little bit arbitrary, but what's really cool about it is that once we do all of it, now all of a sudden all of the edges that will be cut will have two link intervals and they'll just be two different colors. And all the e-gadgets that will not be cut have link intervals that are the same color. And so now we can consider what the max cut of this is, and we can get whatever the max cut of this entire graph is. Unfortunately, it's not super clear because the value that you get is very, very long and has all of these terms. But all of these terms are actually just due to the construction of the graph. And really, like we can kind of ignore them just like at first, and we can just consider this 2x q prime. And x is the cut size of this cubic graph. So here x is equal to 4 because there are 4 edges that will be cut here. And yeah, so let's just take a look and like see how many edges will be cut in this interval graph, knowing that we have exactly 4 of these guys that will be cut. So once again, let's just zoom in on this pink guy and see what he has to say. So let's now consider like all of the different edges that will be cut between all of these link intervals and all of the e-gadget intervals. So one edge that will be cut will be this one that connects this one with this up here. So let's go and write that down. So we have, this value is going to be q, due to the construction of the gadget. So there are q intervals that are all intersecting with this link interval. So therefore we have like q contributing between this one and this one. And next we have this next one right here. So we have all of these left short intervals that are intersecting with this yellow one. The cut contribution will be q plus p. If there's a moment where you have link intervals that are colored in 2 different ways, then all of the edges that will be cut between between the link intervals and the v gadget, not including all of the edges that will be cut within the gadget or the edges between the link intervals themselves, only just between the link intervals and the e gadget. The cut contribution will be q plus p. And this holds through for every single one of these cut e-gadgets. The contribution of the cut between the link intervals and the e-gadget is always going to be q prime plus p prime. Let's instead look at now the case when we have 2 link intervals that are on the same side. And let's see what happens when we compare it to an e-gadget. So in this e-gadget, so we see that these left short intervals are going to be intersecting with this link interval right here. And that is actually the only intersection that happens. Therefore, that's the only edge that's going to be cut. So the only edge that will be cut will be just p prime. So so we can say like p prime So here I'm writing out all of the contributions to the cut, depending on each e-gadget. So we see that the cut is always going to have a p in it, like no matter if it's cut or not, but it's only going to include a q for all those edges that are cut. And since that's true, we can kind of shorten this to saying, if we let like m be number of edges in the cubic graph, then we could like simplify this with its or p prime times m, but then plus only x times q prime. And that's where we get this x q prime up here. But here we actually have 2 times x q prime. And the only reason that there's this 2 times is because it makes the math a little bit easier. So they decided to just multiply absolutely everything by 2. But ignore that. We can just divide this whole thing by 2. And and we see that that's where this x q prime comes from. Yeah, I could go through and like prove all of these smaller cases, but they don't represent, or they don't change depending on what the max cut is. So I'm going to leave it out from this talk, but I have linked the paper in the email I sent out. So if you feel like going through why you have like this 3n over 2 and like all these random terms in here, you can go through it on your own. But really, like, this is the only important term, is this 2x q prime, or in this example, x q prime. Here, yeah, I'm changing everything that we did slightly, and now I'm going to show you what like the actual paper does, and it has every single link interval actually just be like 2 link intervals. So this is where we get like that multiplying by 2 I was talking about. It makes the diagrams like way messier, but it makes the math way easier to just do that. So now that we're kind of done with the diagrams, I'm gonna, now start dealing with everything times 2. So this is where we would like put times 2 and then times 2.
So Isan?
Yeah.
The thing that I'm wondering about is the following. So far, I don't think you have spoken about the cut edges that are contributed between the link intervals and other link intervals.
Mm-hmm. Right.
Right. So in particular, when we're doing like the backwards direction, right? What can happen is that like you can get some additional edges by basically like balancing who of those guys gets yellow and who of them is not yellow, and you can be winning or losing something based on that. So how does the paper sort of handle that effect?
Right. Yeah, that's exactly what I was going over next. So here we are deciding our P's and Q's. Mm-hmm. And step 1, so if you notice here, so there are 6n different link intervals. That is because each one of these V gadgets, and there are n V gadgets, each one of these has 6 link intervals attached to it. So there's 6 here, 6 here, 6 here, 6 here. So there are 6n link intervals. And if you notice, every single one of these link intervals intersects with one another, forming a clique. And this clique will be size 6n. And since it's 6n, its max cut size is going to be 6n over 2 squared, which is equal to 9n squared. Because just the solution to the max cut on a clique is n squared over 4. And in this case, yeah, we would get 9n squared. So therefore, like this is saying that if we were to perfectly balance all of these link intervals into some like specific way to like try to maximize the max cut of all these link intervals, the highest possible value that we could get is 9n squared. So yeah, like Daniel was saying, if we were to try to like, oh shoot, actually be better if we like colored one of these like differently, the highest possible value we could get is 9n squared. And so the paper realizes this, and it sets every single one of these Q's and P's to be way larger than n squared. And since it does that, the link intervals are entirely affected by these gadgets. Since these gadgets are so large, they are like forcing the link intervals to take this shape, just out of the way that we've chosen our P's and Q's and P primes and Q primes. Now the link interval just must take this coloring. And to be honest, like the paper was not super clear in how they did it. It's very like hand wavy. It's like, oh, right, since like this is that, then therefore this is that. So I'm not entirely sure how they derived that, but yeah, but it's using this inequality, and it also throws in this inequality, and it talks about how. So it says that from the way that we've chosen the P's and Q's, now the partitioning of the E gadgets is completely determined by the partitioning of the V gadgets. Because yeah, you see here like the P and Q's, meaning the V gadgets. So this is for the V, and then this is for the E. The V gadgets are way larger than the E gadgets. So therefore they have like a bunch of say, and their contribution is way larger than these guys, than the E gadgets. So the E gadgets like have to do what the V gadgets say, just because of the way that they've chosen these numbers.
Cool.
And therefore, since we know what this coloring is, like because of the way that we've chosen our P's and Q's, now we know that the coloring must exactly take this shape. And when I say the coloring, I'm saying that the max cut must take this shape. And since the max cut must take this shape, then therefore the backwards direction holds, because then we just find out whichever link intervals have two of the same or two different for each E gadget.
What the paper does is, if you consider these vertex gadget and edge gadgets, right? They say that if you consider any, any max cut, so there what happens is any vertex gadget or edge gadgets, all the left small intervals will always lie in the same subset, and all the right small intervals will lie in the same subset. Similarly, they prove all the long left intervals will lie in the same subset, and all the long right interval will lie in the same subset. And further, they also say that a left small interval and a right long interval, both combined, will lie in the same subset, and the right long interval and left small interval will lie in the same subset, but it will be opposite. So basically, if you take any max cut, the possibilities of a link gadget, it's fixed. There are only two possibilities. It's either this or that. So there are no four. They prove that there are only two possibilities. And now the cut edges inside the gadget is so small, between the vertex gadget and edge gadgets, and also between the link gadgets is so small that it doesn't matter. The only thing that in the end that matters is the edges between the link gadgets and the vertex and edge gadgets. Yeah. So essentially, there's only two choices. There's not four choices. So in any max cut for a link, for a vertex or edge gadgets, there's only two choices. That's what they proved. And yeah, that was kind of the main lemma.
Okay, all right. I think done. Okay, thanks.
All right. Yeah, that's the gist of the paper. There's a lot more. This is like a 10-page reduction. I'm really sorry if I went fast or if it's completely went over your head. I've read it about 6 times at this point, and I still only understand about 80% of it. So I really apologize if it was weird. But if you have questions, feel free to ask away.